All right. Lecture 9, VCE Specialist Maths. We're going to look at proof techniques. So these are some of the ideas we'll cover: divisibility of integers, Euclidean division, conditional statements, direct proofs, negation of statements, De Morgan's laws, proof by contrapositive, proof by contradiction, and the converse of a conditional statement. So if you are keen to learn about those things, then stick around. As always, as well, if you're finding these videos useful, please consider subscribing or liking. It might be a small thing for you, but it means a lot to me because, yeah, trying to grow the channel and reach as many people as possible. So let's jump into it. So let's look at the divisibility of integers. So if we have two integers a and b, then we say that a is divisible by b if there exists an integer k such that a equals kb. So let's just look at this example just to sort of clarify things. Let's just say a is 12 and b was 3. Well, does there exist an integer such that k times b equals a? Well, I think you would agree that k would be 4. And so we would say the following. We would say that b is a factor of a, or 3 is a factor of 12. So that makes sense. B is a divisor of a. So 3 is in fact a divisor of 12. That makes sense. And a is a multiple of b. Yep, 12 is a multiple of 3. So that checks out. Okay. Euclidean division is basically that same idea. We're just sort of introducing remainders. Excuse me. So again, if we have a and b as integers, but b is not equal to 0, then there are unique integers q and r such that a equals qb plus r, and r is between 0 and b. Let's just talk about that a little bit. So again, let's say that, well, not again, but let's say a is 13 in this case. And we're going to say, okay, 13, I think you would agree, is equal to 2 times 5 plus 3. So Q is 2, B is 5, and R is 3. So we'd say that therefore Q is 2 and R is 3. I think you would recognize by now R is the remainder. If we were to take 13 divided by 5, we would get 2 remainder 3. And sort of just this last part here is saying, okay, your remainder is always going to be greater than or equal to 0. If it's equal to 0, you've got no remainder, which means it is a factor, right? And it's less than the absolute value of b, okay? Because if it was equal to b, then it would also be a factor. I think you would agree. So, yeah, that is what Euclidean division says. It's just this idea of, yeah, factors, divisors, multiples, all this sorts of terms we spoke about here. Okay, let's have a look at the next thing, which is conditional statements. And a conditional statement is an example like this. So if a person is a teacher, then they work in education. So we call P, this first statement, our hypothesis. So if a teacher is a person, that is our hypothesis. Then they work in education. So that's Q, which is our conclusion. Person works in education. So this is what we call a conditional statement. And in logic terms, we abbreviate this as P implies Q. So we read this with this arrow as P implies Q. I think that makes sense in this example. If a person is a teacher, then they work in education by definition, right? Okay. Then what we can do is we can start to talk about proofs. So what we might want to do is to show that a conditional statement is true. What we're going to do is assume that the hypothesis P is true, and then show that the conclusion Q follows. So it makes sense with an example here. If a number is even, that's our hypothesis, then it is divisible by 2, which is our conclusion. So what we're going to do is we're going to assume that P, which is the hypothesis, is true. So that means that the number is even. So we're going to assume that it's even. And by definition, we know that an even number can be written as n equals 2k, where k is an integer. And that should make sense. Our number is a multiple of 2 if it's even, right? So then what we can say, since n equals 2k, it is clear that n is divisible by 2, thus q, which is the conclusion, follows, and the statement is proven. So that is an example of a straightforward direct proof. Assume that the hypothesis is true, and then show that the conclusion follows logically from that. All right, let's have a look at the next thing. Okay, we're going to look at the negation of a statement. So, for example, all dogs are animals. So that's a true statement. To negate that statement, we're going to say there is at least one dog that is not an animal. And I find this stuff can be a bit confusing. If you just saw this statement, all dogs are animals, and you were asked to negate it, you might negate it by saying all dogs are not animals. But that's making a universal claim that we actually don't need to make. All we need to do to say that this isn't true is say that there is at least one dog that is not an animal. So this is how we negate a statement. In this case, we've shown that there's an exception to that rule. Let me make sure I phrase this right. So we haven't found we've stated something that isn't true. So there is at least one dog that is not an animal. That's obviously not true, and that's the correct negation of that statement. All dogs are animals, which is true. Okay, and then what we can introduce is what's called De Morgan's laws. So De Morgan's laws are fundamental rules in logic and set theory that describe how negation interacts with conjunction, which we call and disjunction, which is or. I'm most familiar with set theory, so I wanted to show it using sets because we've studied a bit of probability together. And let's just look at this notation first. This says P and Q not. So we're basically in this Venn diagram, we've shaded in everything that's not P and Q. Remember, P and Q is this inside part here, right? So everything that's not that is everything on the outside plus everything in here and everything in here. Okay, and what De Morgan's first law says is that P and Q not is the same thing as not P or not Q. Okay, now let's think about that. Not P or not Q. So imagine this was all unshaded for now. Not P. Well, not P would be everything. So it'd be everything in this Q, not including P. So everything in here and then everything on the outside. And then, or, so we're adding on not Q. So that would be everything inside P, not including the inside, and then everything on the outside, right? So you can see and get a pen and paper out and draw it out if you need to, but P and Q not is the same as not P or not Q. So if we look at an example here, we could say Peter is punctual and Quinn is quick. So P is that Peter is punctual and Q is that Quinn is quick. All right, the negation of this is that Peter is not punctual or Quinn is not quick. So that is the correct negation of this statement. Remember, our use of the word and here is very particular. Peter is punctual and Quinn is quick. Correct negation of that using this logic is that Peter is not punctual or Quinn is not quick. Okay. Let's have a look at De Morgan's second law, which says not P and not Q is equal to not P is equal to P or Q not. Okay. Again, this is sort of how we would show that shaded in. Not P and not Q is everything that's going to be on the outside, so that's sort of shaded in. But I think you would agree, P or Q, the complement of that, P or Q is everything on the inside, P or Q is everything on the inside of the circles, not that, so that's just on the outside. So you can see why these are true. Okay, and again, if we get given a statement, Peter is punctual or Quinn is quick, this time it's or, so it's the disjunction. The correct negation of this is Peter is not punctual and Quinn is not quick. Personally, I still find it difficult to sort of really grasp why that's true. To me, this is just something I've learnt. But Peter is punctual and Quinn is quick. Apparently, the opposite of that is Peter is not punctual or Quinn is not quick. It's not necessarily obvious in my mind anyway. Maybe it is to you. But yeah, those are De Morgan's laws. Okay, let's have a look at the next thing. We're going to look at what's called proof by contrapositive. So what that means is you swap the hypothesis and the conclusion and negate both. And then that's what's called the contrapositive. Probably should have just read it. By swapping the hypothesis and conclusion, negating both, we get the contrapositive. So for example, if a number is divisible by 4, that's our first thing, P, then it is even, Q. So hypothesis conclusion, so P implies Q. Okay, if a number is not even, Q, then it is not divisible by 4, P. So we would say not Q and not P. So this symbol here, actually don't need to know this for the specialist course, but this is how you would write it using logic. Not Q implies not P, which is the contrapositive of this situation here. Swap them, make them, negate them. So if the original statement is true, then the contrapositive is true. If the original statement is false, then the contrapositive is false. Okay? So this is helpful for this reason. This means that we can prove a statement is true by proving the contrapositive, which is often easier. So let's look at an example and it'll make more sense. So if n is even, then n squared is even. All right, let's think of the contrapositive. We're going to swap them. So I'm going to say if n squared is odd, because we're negating it as well. So it says that n squared is even. I'm going to swap it. Q becomes P. Or rather, we swap P and Q. So we say n squared is odd now, which means not even. Then n is odd, which is not P. Okay, so what we can say is, all right, to show this, we can say, all right, let n equal 2k plus 1, where k is an integer. Now, 2k plus 1 must be odd because it's one more than a multiple of 2. So we get this. So that's n, and we're all right. So let's say n squared now. So n squared, we take this, we expand it, we get 4k squared plus 4k plus 1. Take a 2 out as a factor. So it's 2 times this thing plus 1. So we can see we've proven the contrapositive, which proves the original situation. Okay. Okay, so now we're going to look at proof by contradiction. So proof by contradiction is this. You begin by assuming that the statement we're aiming to prove is not true. Demonstrate that this assumption leads to a logical inconsistency or contradiction. Conclude that the initial assumption must be incorrect. Deduce that the original statement is therefore true. Okay, so here's a classic example of a proof by contradiction. So prove by contradiction that x is irrational if x satisfies 3 to the x equals 7. So firstly, assume the opposite of what we want to prove. The statement we aim to prove is not true. Yeah, so suppose x is rational. Okay, so that's doing this first step. Okay, express x as a ratio of 2 integers. Remember, rational means it can be expressed as a ratio of 2 integers. So we get x equals p on q, where p and q are natural numbers. Now what we're going to do is we're going to take that, I'm going to substitute it into this equation. 3 to the p on q equals 7. Applying some index laws, we get 3 to the p multiplied by 1 on q equals 7. Now this step might be a little bit confusing, but if we've raised 3 to the 1 on q, we can move that to the other side, and then we'll get 7 to the q. Think of it like this. 3 to the power of 1/2 is the square root of 3. Move it to the other side. It becomes, you're squaring it on the other side when you undo the square root. So undoing 1 on q is raising the other side to the power of q. Okay, and then analyze the situation. So 3 to the p is a power of 3. Okay, that makes sense. 7 to the q is a power of 7. Okay, 7 and 3 are co-prime. So what that means is they don't have any common factors other than the number 1. So the assumption that x is rational leads to a contradiction. Therefore, x must be irrational. I just want to explain this in a bit more detail. To be a power of 3 means that its prime factorization would be entirely 3s. It'd be 3 times 3 times 3 times 3 times 3, and so on. And similarly, since 7 to the q is a power of 7, its prime factorization would be 7 times 7 times 7, however many times, q times, right? Nowhere in there you're going to get a common factor. So 3 to the p equals 7 to the q is not right. So therefore, x must be irrational in order for this to be true, because we assumed before that x was rational, and then we proved it by contradiction. Okay, so So that's that idea of proof by contradiction. Now, the last one, the converse of a conditional statement. So I think this is a good example. Statement, if a shape is a square, then it is a quadrilateral. Okay, the converse of this is if a shape is a quadrilateral, then it is a square. Okay, so we can see that this first statement is true. Shape is a square, then it's a quadrilateral. If we take the converse, basically swapping them, then we get something that's false. But it may not always, a true statement doesn't necessarily always become a false statement when we take the converse. So the converse of a statement may not be true. So if the converse of a true statement is also true, then it is what's called biconditional. And this is the notation where we would use P implies Q, Q implies P. So, for example, here is a biconditional statement, also known as an equivalent statement. A polygon is a quadrilateral if and only if it has four sides. So just think about that for a moment. Always pause and think. Polygon is a quadrilateral if and only if it has four sides. That's true. It has to have only four sides to be a quadrilateral. All right, the converse of that would be a polygon has four sides if and only if it is a quadrilateral. That's also true. And I encourage you again to think about that. A polygon has four sides if and only if it is a quadrilateral. This is what's, yeah, these two statements are biconditional, also known as equivalent statements. And what we also need to know is to sort of wrap things up is to prove that two statements P and Q are equivalent, you have to prove two things. P implies Q and Q implies P. So you need to show, yeah, that both of these things are true to show that your statements are equivalent or biconditional. Sometimes we just refer to it as if and only if sort of statements. Okay, logic is tricky, but it's a really cool way to think. So I'm going to do some more videos on this type of stuff. And as always, happy studies, and I'll talk to you soon.